Okay. All right. So hopefully not too many people are in the classroom. Right, so kill a little bit of time. So today what we're going to be doing is we are picking up where we're talking about slopes of tangent lines. So we'll call a little bit of that, but the big thing that we're talking about today is how the same limit, that is the slope of the tangent line, also has other uses, which is really why it's so important. And while the slope of the tangent line is a nice graphical picture which connects a lot of geometric and algebraic ideas that you've encountered before, the real reason is not that we're so enthralled by slopes of tangent lines, it's that that same quantity has a lot of other uses, and that's just kind of one nice way of introducing the ideas. So what you can do is, so this video is going to be posted on Canvas after we're done, and the lecture notes that I'm working off are posted on Canvas now. It's a bit of a big file, but it's there so you can follow along or go back and look things up after we're done. So let me mark some of the people who just came in. Okay. And then, all right, let's get into it. This one. Okay. So as a quick recap of the ideas that we really got into in a more serious way last week. So we're talking about the slope of the tangent line. Where that comes from is, given the graph of a function, we can look at slopes of secant lines between some fixed point a f of a, we think here, and some point x f of x, which we think of as movable. And the slope of the secant line is given by the slope formula f of x minus f of a over x minus a for these particular kind of points where the y coordinates are always the function value at the first coordinate. And the two ways we can think about this are, let this point x get closer and closer to a, or let the distance between these 2 points get closer to 0. And either way, there's a limit which corresponds to this process of taking the secant lines, and as this point moves closer and their distance goes to 0, the secant lines get closer to the tangent line. So the slope of the tangent line is the limit of these slopes as you let your moving point get closer and closer to the fixed point A. Or letting h be the distance and letting the distance between the points go to 0. So our points become fixed point A, and then a plus h is a, but you moved a little bit by some tiny number h. Then the slope of the tangent line is the limit as h goes to 0, so the distance between the points goes to 0, of f of a plus h minus f of a over h. So this is what we saw some last time. But what we also indicated was we were talking about this height of the drone and how fast is it moving, was that the ideas we used to analyze this drone's motion were really the same as our first pass through understanding the slope of the tangent line. And so if we look in that context, so we have a function giving position. So here we're thinking of there's some designated position 0, and this says after t seconds, how far away are we from that position? Often we start at this point where we're seeing how far are we from our initial position, but sometimes maybe you start 2 feet to the right of the initial position. Anyway, so there's some function telling you what your position is over time. And then the average velocity on an interval is the change in your position, f of b minus f of a, divided by the length of the time interval that you're moving over, b minus a, which looks exactly like a slope. And so making a similar move, if we want instantaneous velocity, so this is velocity at a moment, not over some range of time, we're going to use the same limits we did when we went from secant line slope to tangent line slope. And either of these limits work. They give you the same answer. The work is slightly different, but it's up to you which one you like more. And we saw that this worked because when we try to approximate instantaneous velocity, we said, well, if we look over shorter and shorter intervals, there's less time for this object that's moving around to do much else beyond what it's doing at this moment A. If you have a long interval, it can maybe speed up and slow down, messing with its velocity, but over a short interval, it really doesn't have a lot of time to change what it's doing besides what is happening at A. And so given that instantaneous velocity is represented by these limits, problems that ask what is the instantaneous velocity of some moving object, it turns into write down the corresponding limit and then compute the limit. So for instance, if we have some particle moving in a line, if you want to picture this, it can be there's a little charged particle in a magnetic field and it's being moved back and forth in a line by this field. Things moving in a line, it just simplifies the situation. We're moving in 2 dimensions. There could be other questions you might ask. So this thing's moving in a line and its position in centimeters after t seconds of this movement is given by this formula 3t plus 1. So this formula tells us where the particle is after t seconds. But we could ask, how fast is it moving at any time? In particular, how fast is it moving after 4 seconds of whatever our little experiment here is? And if we want to find this, then we use these limits for this function f and this moment a. Those are the f and a that appear in this limit. I'll use this second version. So a step which isn't strictly necessary, but can be good at least at first for sure until you get used to this. We write down the limit that we want, which is this form right here. But instead of this a, we're using our particular 0.4. So that's what we're doing here. Why it can be good to write this down is because this really tells you exactly what you're supposed to put on the top here. So first up, f of 4, this is going to be the number you get when you put the number 4 in for t in our function and then compute that. So if you put t or 4 in for t, you get 3 times 4, which is 12, plus 1 is 13, and that's where this 13 comes from. So this f of 4 is this 13 being subtracted. For the other part, we're finding f of 4 plus h. What is happening here is this says whatever you're putting in here, 4 plus h, that is being substituted in for this t. So let me pick a... So this 4 plus h is going in for this t. So instead of t times 3 plus 1, here it's going to be 4 plus h times 3 plus 1. And it doesn't simplify to be a number yet because there's this variable h in here, but you're doing the same thing you did with the 4. You're just left with an expression that has an h in it. Before we totally move on, are there questions about why this is the limit that we really are going to want to compute to answer this question about instantaneous velocity? So once we have this limit identified as the thing that we really want to do, now we can forget about this instantaneous velocity and really just say this is a limit. We've been doing limits for a while now. So let's go ahead and compute this. And the things to expect in these limits are the things that show up in, or in this limit, show up in a lot of limits. What'll happen is anything on the top that doesn't have an h is going to cancel out. And once everything on the top has an h, we can cancel it with the bottom h. So how that looks in this particular case is, well, the two simplifying things we can do are first, multiply this 3 times 4 and h to give us 12 plus 3h. Then also this 1 and this negative 13, those are numbers, so we can combine those to get negative 12. And here's where what we expected to happen actually does happen. This 12, drawing tool, this 12 and this 12 can pair up and cancel out. And that's what you want to see. Things that don't have h's get paired up with something else that doesn't have an h, and they cancel by adding up to be 0. And if that isn't happening, then you should think, maybe I did something wrong. And you need to go back and see where that happened. And so after everything that doesn't have an h cancels, we're left with just this 3h on the top. And here, the simplifying is a little strange, just because there isn't a lot going on, but this is what we expected to happen. Everything on the top has an h, so we can cancel those h's, and here we're left with just the 3, which in this case just means now finding the limit's really easy. 3 is a constant, so you can take the limit, you get 3. Questions about computing this limit and getting this number out? Okay. One observation that I want to point out before we move on is something that really says this slope of the tangent line thing is makes some sense. So the observation is, if you look at the function we started with, 3t plus 1, this is a line with slope 3. And what happens is, if you think about the tangent line context that we've been thinking of here, if you try to draw the tangent line, you really get the same line that you started with. So most of the examples of tangent lines that we'd been looking at would say we have some kind of curve like this, and then we would draw its tangent line as something like this, some line which kind of just hits the graph. But if your green thing is a line, then there's no sort of curve for you to just hit and then go away from. If you try to draw the tangent line when you start with a line, you really just try to go over the same line again. So if I said, here's this curve, draw the tangent line for this at this point, you would just draw on top of this line. So that means this 3 that we got, or what's happening here is this 3 that we get is the slope of the tangent line here, but it's also the original slope of the line that we started with. So this complicated way of finding a slope gives you the same slope that you could just read off of a line, which is good verifying that things fit together in a way that it seems like they should. This is also a little indicative of where we'll try to get to eventually is finding faster ways of finding these slopes. So for instance, in this case, if you said, here's this line, or here's this function, we'll eventually get to the point where we're saying, well, this is a line, its slope is 3, that's going to be the velocity or the slope of the tangent line, that quantity that I'm looking for. So even beyond velocity and the slope of the tangent line, in general, if you have any quantity which is changing, so velocity, that really corresponds to height or position, but it could be population, temperature, costs, profit, I don't know, the area consumed by wildfire, the number of people infected by a certain disease, any quantity which is changing, and you want to know how fast is it changing? How quickly is the population increasing or shrinking if your town is getting smaller, for instance? How fast is a disease spreading? By how is the number of people infected changing? Anytime you have a quantity which is changing, the instantaneous rate of change of that quantity is represented by this limit. Arrived at through really the same way that we got to instantaneous velocity. You can talk about average rate of change of some quantity, which is a slope looking expression. And then taking a limit says, find the average rate of change over a smaller and smaller interval of time. And that corresponds to taking a limit, and the limit you get is the instantaneous velocity or instantaneous rate of change of this function at a point. So this is really why this quantity is worth talking about. This thing which we first saw as the slope of the tangent line, in fact, corresponds to rates of change of any quantity you want that you have a function for. And maybe more generally explains why calculus is so important, because anytime you want to understand how something is changing, the right way to do that is with calculus. So what we need is some better terminology. I've been saying this kind of limit, the limit we've been looking at, and we need a word for that. So the terminology that we'll use is that we'll say the derivative of a function f at a point A is written like this. So it's f with this little kind of apostrophe looking thing. This is read f prime of A. So f prime is saying you have this function f, but we're not thinking of values of the function, we're thinking slope of this function's tangent line. So f prime of A, which is the derivative of this function at a point, is how we will refer to these limits. And like before, these two forms of the limits are equal, just the actual calculation will be a little bit different. And also worth pointing out is this quantity, the derivative of a function at a point, is a limit, so we have to throw on the caveat if this limit exists, because we've seen that limits don't always exist. And we need to be aware of the fact that you can write this limit down, but it doesn't necessarily correspond to a number. So this terminology, the derivative of a function at a point with this notation f prime of A, that's what we'll take as the quantity we're interested in. And so this f prime of A is the instantaneous rate of change of a function at a point. In particular, this represents the instantaneous velocity for some position function at a point A. This also represents the slope of the tangent line of a function at a particular point. And it also gives us a nice way of saying we can write out an expression for the equation of the tangent line. And this is point slope form. This is y minus the y coordinate of this point is equal to the slope, f prime of A. This derivative at A is the slope of the tangent line, and then x minus the x coordinate of our point A. So this is a kind of nice succinct way of writing this down, but it's a little deceptive because this expression here is saying figure out what this limit in either of these formulations is. And that number that you find, that's the slope that goes here. So it's nice having some notation to make writing this out easier, or to say what I want to find without using a bunch of words. But the computation for finding it is still figure out the appropriate limit and then find that limit. So as far as examples of finding the derivative, look back at any of the examples that we've done. Any example where you had to find instantaneous velocity or the slope of the tangent line, in those cases, you were finding the derivative. They're all different words for the same quantity. Okay. Sorry. Another way of thinking about the derivative is that when we're right here, we're talking about the derivative of a function f at a point A is this particular limit. But another way to think about this is that what if you fix your function f? So you have a particular function in mind. And then you could say, I want to know the derivative at a bunch of different points A. So you pick some point A, and that shows up in your limit, and it affects the value of the limit. And as you would imagine, if you pick a different point A, you get a different limit, which gives you, or you get a different limit to set up, which gives you a different limit value. And this also happens if you're thinking about slope of the tangent line. If you have a particular function in mind, so let's draw one. You have a particular function here. If you pick different points on this, so you have some point here, some point here, some point here, you get different slopes. Here, the slope is going down a little bit. Here, the slope is really steep. Here, it's also going down a little bit. So the value of the derivative depends on which point you pick, because it's the same thing as if you pick different points along a curve, they have different tangent lines with different slopes, and the slope you get depends on where you picked the point. So the derivative of a function at A is you picked a particular point A, and you found this limit, which corresponds to the slope of the tangent line. But if you pick a different point A, you're going to get a different number. And that correspondence is like a function. So that's another way that we can think of the derivative. So this is really what I was saying there. If you pick a point and ask for the slope of the tangent line, the slope you get depends on the point that you pick. So there's really a correspondence here that says you pick a point, so you fix some f in the background, then you pick a point, and then you can kind of output the slope of the tangent line of f at the point that you chose. So rather than thinking of the derivative at a point being a particular slope, we can kind of think of them all at once as a function. So this is another kind of perhaps more important way of thinking about the derivative. So for a function f, you can define a new function f prime, where how you compute the value f prime at a particular x is you use the x that you're given, you set up this limit, and then evaluate it wherever it exists. And the function defined this way is called the derivative of f. So on the last page, what we were saying was you have a function, you have a point, you use those to set up this limit, and that gives you the derivative of the function at the point. How you can also think about this is that you pick the point f, and you can say for any x, you can compute this limit, and that defines a function. You give me the x, I'll tell you the slope of the tangent line at that point. And that correspondence is what we'll call the derivative of f. And so where we'll get to will be given a formula for f, we will find a formula for f prime. And what that will allow us to do is, rather than having to write down a limit every time we want the slope of the tangent line, we can say we have a formula here that says you pick the x where you want the slope of the tangent line, put it into the formula for f prime, and what you get out is the slope of the tangent line. So if you have this a formula for this f prime, which really takes care of this limit process all at once, then finding the slope of the tangent line anywhere is easy because you just put it into this formula, rather than writing down a limit every time. So that's where we'll want to get to. Before we get there, a few things. First is the derivative, either the function, the derivative, or the derivative at a point. It's really important. Like I said, anytime you want to talk about quantifying how something changes, the derivative is the way to do it. The derivative is also a really old idea. Calculus was invented in the 1600s by Isaac Newton and Gottfried Leibniz, a German mathematician. If you look it up on, say, Wikipedia, there's a lot of drama over who really invented it. And it's a big deal about who was the real inventor of calculus. But the ideas had been around like 100 years before. They just kind of formalized it. So calculus is really important and really old, which means that there's a lot of different notations that have shown up around it. And these aren't even all of them. Physics has its own kind of particular thing. But some other notations for the derivative. So f prime is the main one that I'll use. But if you have your function f prime, if you write it as an equation, so this would be something like y equals 2x squared plus 6, where you have an equation like that. The derivative could also be represented as y prime for your y equals stuff with x equation. A really different looking notation is this dy dx and df dx. The point of this is, well, first of all, it's not a fraction. You don't split these pieces up. It's just a single piece of notation, which is supposed to say delta, which is a Greek d, gets used for change in and often appears in the slope formula. The d here is supposed to indicate there's some sort of limiting process going from delta y over delta x, these slopes, to dy over dx, the slope of the tangent line or instantaneous velocity. Another way is this last one, which is really meant to say, given some formula, finding the derivative is a process. And it's almost like you input a function to the derivative finding machinery and you output another function. And so that's what this is kind of indicating. Also, if you want to evaluate the derivative at a point, these middle two fraction looking things, really all of these other than the f prime of x, they don't have a good place for the point. So f prime of a, there's a nice place for the number a to go. If you have one of these other ones, sometimes this vertical bar where it says, where this is right, evaluated at x equals a. So there are a bunch of notations that get used with a derivative. I'll be using some of them just to get you used to them a little bit, but there's nothing really deep about them. They just get used different places, and it's something you get used to, that these different notations all mean the derivative, which is the function given by this limit. So something more important, the notation is just making you aware of it because it's going to show up. What is also important is that there is a relationship between the function and its derivative. So, for instance, we can think about how does the graph, if you have the graph for a function, what does that tell you about the graph of the derivative? So this f prime of x says input x, find the slope of the tangent line of this original function, and the number which is that slope. That is the output value for this derivative. So first up, we can estimate some values of these slopes. We can't get exact values, not least of the reasons why, because I didn't give you a y axis here. But we can get some rough ideas of how this graph of f corresponds to this, which will be the graph of the derivative. So the first thing you can ask about is, if you look at these points at 1 and 4, so at the bottom of this dip and the top of this hill, if you graph the tangent lines, they are horizontal. So it's curved, but at this part, the graph's tangent line is flat. And what is the graph of a horizontal line? And not rhetorical. What is the graph of a horizontal line? So the slope should be, so we're looking for a number here. So what is, for a horizontal line, the slope is, right, so the slope is 0. If you pick 2 points on a horizontal line, the change in y, they have the same y value because it's horizontal. And so the top of the slope formula is 0. So what we can take away from this is that at these 2 points, 1 and 4, the tangent lines are horizontal. Horizontal lines have slope 0. So because of these 2 horizontal tangent lines, that is why our derivative is 0 at these points. The value of the slope is 0, so those are the output values of the derivative. So even though the function is above the x-axis here, we're not looking at how high the function is, we're just looking at what the slope is. And so the fact that the slopes are 0 at these 2 points says the derivative is 0 at these 2 points. Does that make sense? Okay. And so those are good points to start with, because finding horizontal tangent lines is something which, those are a little more easily identifiable. These points where the graph is sort of flat. But what we can also see is if we look between these 2 points, so for this region here, if you draw any tangent line at a point along here, the tangent line is going to be going up. And a line which is going up, while you don't know exactly what the slope is, you know for sure that the slope is positive. So between these 2 points, everywhere the slope is positive, and the derivative is the value of that slope. So this part here, which is we're thinking of as moving up, or draw any tangent lines and the slopes are positive, that explains why this part of the graph is above the x-axis. So here, the derivative is positive, which means this corresponds to the slopes of the tangent lines being positive on this part. And on the outsides, we can have sort of similar reasoning. If we look at these colored orange parts of the graph, if you draw any tangent lines at some of these points, I've got a couple examples in black there, every tangent line you draw is going down. So on these 2 orange parts of the graph, every tangent line is going down, which means every tangent line slope is negative, and those negative tangent line slopes correspond to the derivative being negative. So there's this correspondence that we want to try to understand between what the graph is doing and what that means for the derivative. More useful, really, will be learning about what the derivative does to inform what the original function is doing. But this is kind of a first pass at understanding how the graph of the function and the graph of the derivative are related. Last questions before I move into something a little different. Okay. So the last example of the day is actually computing the derivative function. So we'll pick a specific function and we'll write down this limit. What's going to happen though is in here, these x's, those are variable x's which will appear in the limit and will appear throughout our evaluation of the limit. So that makes things a little more complicated because we won't be evaluating functions at points, which gives us numbers that we can combine. So in finding the limit, we're going to have these x's throughout. But why that will be worth it is when we get to the end, what we'll get won't be a number. The end result is going to be a function with x's in it. And what that function will do will say, you give me the number, this is the formula that tells you how to find the slope of the tangent line, without setting up the limit every time. So it's a little bit different, but a lot of the simplifying work in the middle of computing the limit will be the same. And I'll try to emphasize where those similarities happen. Okay. So we'll start with this case. Here's this function, x cubed minus 1. Let's find the derivative of that. So the formula for the derivative, the limit, is going to be f of x plus h minus f of x over h. When we're looking at this, h is going to be the thing actually going to 0. X is being treated a little bit like a constant, where it's not going to 0, just x's are whatever they are. How we deal with this on the top is similar to some ways that we've handled limits of slopes of tangent lines. First up is this f of x. Here we just use the formula x cubed. And that's where we get minus x cubed plus 1. Because we're subtracting, we flip the negative sign, so it's negative x cubed plus 1. But here we're just using the formula. For the other part, this is again similar to something we've done before. We've said we have x plus h inside here. And so that is going to go in for this x right here. So instead of x being cubed and then subtract 1, it's going to be x plus h cubed and subtract 1. Before we get into actually evaluating this, questions about just why this is the limit that we'll actually need to set up. Okay. Then, once we get this set up, now it is kind of similar in a lot of ways to the sort of limits we've done before. First up is multiply all this out. Here the big thing is x plus h cubed. If you x plus h times x plus h times x plus h, multiply it out, you get all of these 4 terms. So you expand this out, but then what happens is that now we want to cancel things. And like we had said before, anything that doesn't have an h is going to cancel on the top. So for instance, this x cubed is going to cancel with this minus x cubed. And this minus 1 is going to cancel with this plus 1. So all of those things pair up and cancel, and these 3 terms left, each of them has an h in them. And that's what you want to see. If you don't have an h, you pair up and cancel. If you do have an h, then what's going to happen is now all of these h's, when we divide by an h, we cancel 1 h from everything. So 3x squared times h, that has 1 h, it cancels, so we have just 3x squared. 3x squared has 2 h's, so when we cancel, there's 1 left. H cubed has 3, so when we cancel, there's 2 left. So we again cancel this h on the bottom, and then once we're here, like before, this is the kind of limit we can find by evaluating. Here, evaluating looks a little strange because h is going to be 0, and the x's we don't do anything with. So in particular, when you put h equals 0 in, h squared becomes 0, 3x becomes 0. 3x squared doesn't have any h's in it at all, so we don't do anything to that. So that is all that's left when we let h be 0. So this thing right here, this is f prime of x. This is the formula that says you want to know the slope of the tangent line of x cubed minus 1 at any point. We'll take that point, put it into for the x here, and the number you get is the slope that you want. So for instance, the slope of the tangent line of x cubed minus 1 at x equals 3. The answer, put x equals 3 and 3x squared. So the slope is 3 times 3 squared. That's 3 times 9, which is 27. And if you want to pick a different number, you want to know the slope at -6, well, you put -6 in here and compute the number, and that's the slope. So what is good about this is now we did this limit work once, we left the variable in, and that means if you want to find the slope or the instantaneous velocity, if this was a position thing, we only had to do the limit once. Now we just put whatever values we want into 3x squared, and the numbers we get are the slopes or velocities that we're looking for. Last questions about this example. Either the simplifying work or the way that we can use it now to find all these slopes without having to set up a different limit every single time. Okay. Then I can stick around for a little bit if you have any questions, but if not, I'll see you either in the lab or I'll see you in class on Friday.